Okay, so we've already gone over how to do loose dot structures. This is the detailed version. I like to jump in and get you guys started, to get you guys moving, right? And then you can go back over it and you can sit there and say, okay, yeah, I got this. Make sure that you got it, okay? So you should always start by counting the number of valence electrons, because that's always are gonna have to be valid, always, right? So what you put in is what you must get out at the end of the day, right? That's always, remember that saying. It applies to just about everything in life, okay? So the other thing is, now, since you guys are familiar with ions, you have to account for the ions. So if you have one extra electron, -1 or minus, then you're gonna add 1 additional electrons. If you're removing 6 electrons, then you need to account for removing 6 electrons, okay? It kind of makes sense. What you put in is what you must get out, right? So if you're putting in an extra electron, you have to account for that extra electron. If you're removing 5 electrons, then you have to account for removing 5 electrons. So you're gonna have 5 electrons less, okay? Simple, give or take?
Yes.
Got it.
Okay, I always start by drawing what I think is gonna be the case. And remember, the one that has the least electronegativity is the one that we're going to be putting in the center. That's going to be your center atom. So if there's 3 atoms, right, your ones that are least electronegative are going to be center. In habit, just remember, if you're carbon, you always go in the middle because you like to touch everybody, okay? You're a little bit of a whore, so. So then, again, you draw your tentative structure, what you think it's going to be, and then you just make the adjustment. You move things around so that everybody completes its octet. If it's an odd number of total electrons, you know that everybody can't complete their octet, but you want to get it to the point where the ones who are the most electronegative get their octet filled first, and then the one that are least electronegative gets close to their octet, but maybe not be able to achieve it. So like when we did the NO, right? And don't worry, I'll show you examples of this. It's all words on paper until you see it, right? So like NO, we know how many valence electrons does nitrogen have?
5.
Okay, and oxygen?
6.
6.
Altogether, that adds up to how many?
11.
Okay, so is 11 an odd number?
Mm-hmm.
Okay, so we established that's 11 is an odd number. So that means that regardless of what we do, we're never going to get to the point where it's going to be, we're going to reach our octet. So we want to make sure that oxygen, who's more electronegative, and how many of you guys looked at your resource sheets? I'll have one more thing to add to the pile, the ones that I hand out. Of course, I left them all in my car, so I don't have mine with me. But if you look at your resource sheet, you'll actually see that oxygen is more electronegative than nitrogen. So in that case, oxygen is going to make sure that it gets its octet filled first. Then nitrogen is going to worry about it. So then that's how we got that whole get up where we have 1, 2, 3, 4. Okay, so that's 7. That's 8 around oxygen, and altogether that should be 11. 1, 2, 3, 3. Let's see, 5, 7. 7 plus 4, 11. Okay, piece of cake.
Mm-hmm.
Okay. And so it's always good just to check it at the end to be sure, count everything, make sure everybody's satisfied. And that's pretty much it. You guys are good?
Yeah.
Okay. So you guys have already drawn ammonia. You guys remember NH3 is ammonia. You should know this one. This is one of the chemicals that you should definitely know, kind of like water, right?
Mm-hmm.
You're going to see ammonia forever. So you guys were whipping this out without even having all of that full knowledge, right? So this is like a piece of cake. So we weren't even worried about doing this one, right? Okay. So let's try this one. Oops, got carried away. Let's try this one. I also got it. Okay, do you want to do it together?
Yes.
Yes.
Okay, so let's start with how many valence electrons we're working with.
So 24.
Okay, let's see. So we have one from hydrogen. How many do we have from carbon?
4.
4.
How many from 3 oxygens?
18.
Oh, I think I did my math wrong.
Okay, so we have 18.
20. Oh yeah, it is 24, right? Because then you add one.
And then we have a single minus charge, so we add one.
Mm-hmm.
So we have a total of 24. So you're correct. Okay, so now that we've done 24, we have 24. Who's going to be my center atom?
Carbon.
Okay, so then what I always do, I just start putting my electrons where they belong naturally. So we have how many for carbon? How many valence electrons?
4.
4.
So we also have this extra one. So I'm just going to throw that one in, put it on top for right now, until I know what I'm going to do with it. Okay, so we also have hydrogen. How many valence electrons does hydrogen have?
1.
1.
We have oxygen. How many valence electrons does oxygen have?
18.
18.
6.
Valence electrons.
6.
We have 6, right?
Oh, duh.
Because there's 3 oxygens.
Right.
Move this to the top. Okay. Okay, so how's it looking so far?
Crazy.
It's looking a little crazy. Let's see if we can make it look a little bit better by moving a couple of things around, right? So we know that we have, in one case, this guy is going to make a bond with this one. So we have this electron. We're going to kick this electron over here. Okay, so then we'll have 2 electrons here. Bless you. Okay. Okay, so is that going to work out for us?
Yeah.
Right now we have 6 around the carbon. And then if we take these electrons and decide to move those over here, is that going to work?
No.
No. So, okay, so damn, this is not going to look too good for us right now. We need to try to figure something out. Well, maybe if I put the, let's say, let's put the oxygen. I'm going to leave those electrons. Leave that 1 electron there, and then bring oxygen's 1 electron, hydrogen, on the other side of the oxygen. Okay. So how are we doing there? How are we doing now? So let's see. Okay, so if I have this electron here, and then I have the one that's left over from over here, bring those together, put those right here. Okay, so is that going to work for us?
Don't you need 2 more atoms around the C?
I do need 2 more atoms around the C. Good eye. So I'm going to borrow those.
Or
So
electron?
then we're sharing a total of 4 electrons. Okay, so does everybody have their octet filled now?
2, 4, 6.
So let's do,
Yeah.
let's do some accounting for. So we have 2, 4, 6, 8 for that oxygen. We have 2, 4, 6, 8 for that oxygen. We have 2, 4, 6, 8 for that oxygen. We have, oops, make square. We have the 2 for the hydrogen. And then we have 2, 4, 6, 8 for the carbon. Everybody happy?
Yeah.
Okay, so the one thing that we want to do is to make sure that we have exactly 24 electrons, because that's how many we should have total. We want to count up all of our electrons. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Got 24?
everybody.
We're good to go. Piece of cake?
Do you still have to like put it in brackets though?
Yes.
Okay.
Good eye. You guys have been, you must have been hanging out with Jessica.
Melissa Maribel.
Melissa Maribel, excellent. Yes, we have to put it into brackets and let me know the charge.
Okay.
So let me know that we added 1 electron.
Okay.
And it was very colorful.
So Dr. Henry, the easiest way to do this is just a bunch of trial and error and erasing.
Yeah,
Okay.
that's the, in all honesty, in the very beginning, that is the best way of doing it.
Okay.
And then you'll get in the habit, okay, carbon goes in the middle. Okay, it looks like I'm probably gonna need a double bond here, you know, and you will find cases where you can make multiple structures, right? And then it doesn't mean that yours is wrong, but usually because of energy concerns, there will be a preference for another structure rather than the other. We're not gonna get into that much detail in this class. The biggest thing is that we wanna just kind of get you in the habit of understanding what the structure looks like. And then because that plays a part in how it's gonna react. Okay.
Okay.
Questions, concerns, Cash? Okay, so before we go, I want to mention this guy is called a polyatomic ion because it is an ion, right? Think about most polyatomic ion, not all polyatomic ion. If you take a look at it, it has hydrogen, carbon, and oxygen. Are these metals or nonmetals?
Non-metals.
They're nonmetals. So they're all nonmetals that are bonding together. They're forming a covalent bond. That's what these are, covalent bond, to sit there and make an ion, okay? So we can have a covalent bond and an ionic bond in one compound. Yeah, see that? So because this guy can react with sodium. So then we'll end up with sodium bicarbonate. Okay?
Okay.
Or sodium hydrocarbonate. Okay. Piece of cake, you ready to move on? Ready for something a little more challenging? Too easy, right?
Mm-hmm.
So you're telling me that the links are helping you guys? Is that my understanding?
Mm-hmm. They help me a lot.
They help you a lot. One other thing. This also brings up another point. You saw how my double bond was down at the bottom and their double bond is here on the side?
Uh-huh.
This is called a resonant structure, meaning that both of these can exist, and they actually can exist at the same time because, you know, we have multiple compounds. Like, you don't just have that one and that's it. You have a lot of them that existing. So I could have my double bond here, and then I could have my hydrogen over here, and so on and so forth. This is called a resonant structure. I'll talk about it again later. It'll be a more clear example. But that basically means that you have the existence of all of those possibilities in your compound when you have a whole bunch of them present, right? If you have one, it's only going to look like one. But reality is, it's like when you get a scoop of sugar or anything like that, or in this case, bicarbonate or hydrogen carbonate, then you're going to have the existence of all of the different resonance structures because they're all stable structures. They're all going to exist, and electrons is really, they're moving. So you could have one at any given point, okay? And I'll explain it a little more in a minute, but I just wanted to kind of introduce resonant structures.
Okay.
Okay, let's see. Resonant structures. Wow. Okay, imagine that. So a resonant structure is two or more equivalent Lewis dot structures for a molecule or an ion. And they're just basically created by changing the positions of the electrons. So a resonant structure is just basically going to be the average it's going to be the average of all of the species, okay? And then, again, I'll show you an example here in a second. The other thing that I wanted to introduce is a resonance hybrid. So that is basically when you have a species that it has the actual structure that is like the average of 2 or more Lewis dot structures. Okay. So you have resonance structures and a resonance hybrid. Okay. And the last thing I want to introduce is an isomer. An isomer is a compound that has the same molecular formula, but different chemical structure. Okay. So same molecular formula, but different chemical structure. Okay. So they also are going to have different physical properties and chemical properties based upon that structure. Okay. So this is an example of a resonance structure. So you guys see we have the double bond located here in this case. We have the double bond located here in this case, and the double bond located here. So these, what was that?
So it doesn't matter where it's located, or it does matter?
No, it does. What I'm saying is that they all exist. In reality, they all exist. They're equivalent to each other, right? A resonance structure is just basically all we've done is the movement of the electrons. The electrons are moving from, instead of being here, they're going to be located here. So that's what this guy is, right?
Mm-hmm. Yep. So it doesn't matter where they are.
Yeah. So in a sense, it's just an average. So what you're getting is you're going to have this one.
Mm-hmm.
We'll call this A. A is going to exist. B is going to exist. And C is going to exist. So all three of them are going to exist. The only thing that's different about these is that the electrons are changing locations in those situations. So that's considered a resonance structure. Okay? Kind of like when we looked at the this guy, right? So I drew it earlier. Oops. So I drew it earlier as double bond O here. Okay, so that's a resonance structure of this guy. Okay,
Mm-hmm.
You see that?
Yeah.
Okay, and now actually let me do it right. Otherwise, Siobhan is going to say, Dr. Turner, what about the brackets? Right? Keep me on my toes. Siobhan. I put an A at your end. I'm sorry about that.
Okay.
Okay, simple. Now, let me give you an example of isomers. Hold on. Maybe. Okay, so this is glucose. This is fructose. So at every point, every corner, there's going to be a carbon. So do me a favor, count all of the points where there's not an element like oxygen here. So there's not going to be a carbon there. So it's going to be an oxygen instead. Count all of the corners here, and then also count that carbon. Okay, and then do the same thing over here. And then count all of the oxygens and all of the hydrogens for both glucose and fructose.
Mm.
You guys can see my screen, right?
Yeah.
Okay.
The carbon, you don't want the carbon, yeah? Use the oxygen and
No, count. I want you to count everything. For both of them, count your carbons and your oxygens.
okay.
So I'm just telling you that each of the points of your polygon, except for this one, have a carbon. So those also count as your carbons. Then I want you to tell me, okay, how many carbons do I have over here
6.
for glucose? How many?
Is it 6?
6. Okay. How many hydrogens?
10.
10.
Let's see. That's 1. That's 3.
11.
Oh,
That's 4. That's 5. That's 6. That's 7. That's 8. That's 9. That's 10. That's 11. That's 12. Oxygen. All of the O's.
1, 2, 3, 4.
We should count in the oxygen, that's by itself, yeah?
Oh, sorry.
You count all of the O's that are here.
Okay.
Can't count. It's too early.
6.
Too early? You're like, I can't count. It's too early.
Wow, like I can't keep track.
Is it 6?
It is 6.
Okay.
Okay. Now over here. How many carbons? So again, each of the ones here, that's 1, that's 2, that's 3, that's 4. Then we have this one here, that's 5, that's 6.
6.
How many hydrogens?
1, 2,
2, 3, 4.
7, 8, 9, 10. 10.
Okay, let's try again. There's 2 here.
Yeah.
That's 3, that's 4, that's 5, that's 6, that's 7, that's 8, that's 9, that's 10, 11, and 12. Remember, that 2 means you have 2 hydrogens, right?
Oh, got it.
Yeah, so don't forget that. So that's 12. And then how many oxygens?
1, 2, 3, 4, 5, 6.
6.
Okay. Now, let's put a big old block over oops. Wrong thing, wrong block. Okay, so we have C6H12O6. How can you tell the difference between the two?
Yeah, the same.
Okay,
You can't. There's no
so-
difference.
you can't, there's no difference, right? So the molecular formula, right, is exactly the same,
Mm-hmm. But the structures are different.
but the structures are different, right? And so that's why the structures are so important for us, especially in organic chemistry, right? So glucose and fructose, they behave differently, right? There's also another form of glucose that actually has it's called a reverse orientation. It's actually a poison. It actually poisons our system. So if we end up taking the wrong form of glucose, we could be poisoning ourselves, right? So those are the things that we want to sit there and take in consideration. That's why it's important for us to understand structure. And so we have to learn how to draw those structures. and have to be able to distinguish between them, right? Because chemically, they look exactly the same, right? If we just look at the molecular formula, they look exactly the same. But if we start looking at the structure, we know that they're different and they're going to behave different.
Mhm.
Okay? You guys get that?
Yeah.
Yep.
Yeah.
And that's also
So
important.
this is an isomer, or
Yes,
what's it?
exactly.
Okay.
This is an isomer. Okay? Piece of cake?
Yes.
Oops. Clear. Okay, so now we get to talk about electron pair geometry. Okay? So remember, we've been talking about those lone pairs,
Mhm.
and it's been itching. So why do we keep track of all those lone pairs? What is so important about these lone pairs? Right? So those lone pairs actually help us explain the shape of those molecules, right? So when we start talking about the structure, we can adjust the angles that two atoms are interacting with each other. So you have that center atom and an atom over here and an atom over here. They're going to sit there and try to get as much space between them as possible, right? Because you want your space. Like if you're not really like dating someone, right? You want your space. You don't want somebody that you hardly know that well sitting right underneath you, do you?
Hell
Well,
no.
Has that ever happened to you where like you get on a bus or something like that and that person literally, I mean, they come into your space or they come and talk to you and they're in that distance that are like right up in your face? It's uncomfortable, isn't it?
Mhm.
Okay, so the electrons are very much the same way. They want to sit there and make sure that they have enough space to, so they're not funking up somebody, so they have room, So they want to sit there and try to ensure that they have room. So they play with angles to try to give them the most distance that they can get from each other. Okay. Now, but they're connected, so there's limitations to how far that they can go. Okay. And so that's what this deals with. So that geometry deals with those angles that we're making. You guys remember angles from geometry?
That was too long ago.
You said no?
No.
Okay. So, well, you're going to have to work on it then, because we're going to talk a little bit about angles.
Okay.
Okay. So valence shell electron pair repulsion theory basically deals with that, right? So those guys, those electrons, are because they're all negative, they can't get too close because they're going to repel each other. And so again, they're going to try to be as far apart as they can possibly be from each other. So they're going to try to maximize the angle that they're far away from each other. And I'm going to talk to you about the shapes that are going to be generated because of that, okay? And so you're going to have to remember those shapes. And actually, if you get that little packet, you got a little handout of those shapes, okay? Okay, so we have what we call the electron pair angle. It's just the angle between two atoms, okay? And so you have your center atom and the angle between one atom on one side and the angle of another atom on the other side. That's going to be your electron pair angle, okay? Or pairs of electrons. So it could be atoms, or it could also be pairs of electrons, those valence electrons, okay? A tetrahedron is basically just a four-sided shape, right? That has equilateral triangles on four faces. Now, this is going to be kind of important because ideally, you're going to have a system where you're going to have four attachments. Like carbon has the most attachments in most cases. We have sulfur under hypervalency, and we have phosphorus under hypervalency. But for the most part, things are going to try to go with that tetrahedral. Hypervalency, it happens, but it's not as prevalent as the tetrahedron, okay? Or four attachments. Okay, so here, if we have an electron here, electron pair on this side, and electron pair on this side, so they're going to try to be as far away as possible. So that they're going to be 180 degrees away from each other, right? 180 degrees is linear, right? A line. This makes a line. Here.
Circle, right?
Okay, so that's good, right? So you guys understand, this is a line. So the angle for a line is 180 degrees. The angle for a circle is 360. You guys remember that?
Mhm.
Yeah.
Yes.
Okay, so circle, 360 all the way around. So together we have this 180 plus 180, that should equal 360. Is that right?
Yes.
Yeah.
Okay, good. So if we have three lone pairs of electrons, 1, 2, 3, it's going to be 120 because they're going to be equal distance apart from each other, right? So 360 divided by 3 is what?
This is
120.
Is 120. Okay. And the other thing is that they're all in the same plane, right? So these guys are going to be all in the same plane. So it's going to be like a piece of paper, right? Flat, one plane. It's not going to be three-dimensional. Where this guy here is going to be three-dimensional, right? And we're talking about a sphere in this case, right? A round ball, okay? So, and we have an electron pair here, we have an electron pair here, electron pair here, and electron here, electron pair here, right? So the angle between all of these is going to be 109.5. Okay?
Yeah.
Okay. And again, remember, it's three-dimensional. Okay? Okay. And you guys probably can't see it. So what I'm going to recommend you guys do, go out and buy a bag of balloons and then do this experiment. Okay? So, bag of balloons, take 2 of the balloons that you blow up, tie it together. What's going to be the bond angle?
180.
It's going to be 180. What's going to be the molecular or the electron pair geometry?
Linear.
Linear, because it's going to be just a straight line. Okay. So take 3 balloons and tie them together.
Mhm.
Have you guys played with the fidget spinners?
Yeah.
The little, you play with them, they spin around and all that stuff.
Yeah.
They're usually 3-pointed.
Yeah.
Okay.
Like a fan. They look like blades from fan.
Yeah. Okay. So in that case, we have 3 things that are attached. So 3 electron pairs, right?
Yep.
Just like these balloons. So, but you look at it, it's like that. It's a flat plane, right? It's all planar, right? So, but there's 3 of them attached. What is the Greek prefix for 3?
Try.
Try.
Tri. So trigonal planar. It's trigonal planar because they're all in the same plane, right? It's flat. And they're equal distance apart from each other, and there's only 3 attachments. Okay, you guys see that? 1, 2, 3. All in the same plane. Okay,
Yes.
this one here, this one is tetrahedral, right? One on top, one coming out towards us, one in the back, and one on the side. It has 4 attachments. 1, 2, 3, 4. What is the Greek prefix for 4?
Tetra.
Tetra.
That's right.
So tetrahedral. Okay, 4. Okay, the bond angle for this is going to be 109. Piece of cake.
We're good. We're good.
Okay.
Okay.
Oops. Okay, so this basically is a table that summarizes everything. So if we have 3 atoms, but there's only 2 attachments. So we have that center atom, and there's only 2 things attached to it. It has no electron pairs at all, right? So the example is beryllium fluoride. So that one is going to be linear. It's going to be 180. So this here is called, the molecular geometry because we're talking about the molecule. This here, if these are just the lone pairs, and this is what this is representing, the lone pairs here, this is called the electron-pair geometry. Okay, so often you'll see EP geometry, and then you'll have molecular geometry. So molecular refers to the molecule as a whole. Okay, so the lone pairs will affect the molecular geometry as well. And I'm going to show you that here in a second. Okay, so trigonal planar, lone pairs. We have 3 lone pairs. So the electron pair geometry is going to be trigonal planar. The angles between them is going to be 120. I'm going to put this in brackets here. Okay, so in the case where we have 3 atoms attached to a center atom, again, you're going to have 120 between it. It's also going to be trigonal planar. The example of this is boron fluoride. Boron fluoride. Or boron trifluoride. Okay, so the case where, again, this represents the electron pair geometry. So you have 3 things attached. And so if you had atoms here, that also counts towards your electron pair geometry. So 3 attachments, 120. However, when we start talking about the molecular geometry, we have, in this case, sulfur dioxide. So in this case, we have a bent structure because we have 2 electrons technically located on that sulfur. It's causing it to be bent more. Okay, so it's going to be bent or angular. Again, the example is sulfur dioxide. For this course, we're only going to go to tetrahedral. Okay. So in the case of 4 electron pairs or 4 attachments, your electron pair geometry is going to be tetrahedral. The bond angle is going to be 109. So in the case of 4 atoms attached, your molecular geometry is also going to be tetrahedral. So you can see your bond angle and your molecular geometry can be exactly the same, right? Depending on how many attachments that you have. And in this case, you're depending on the number of attachments, atoms attached. So this guy is going to be tetrahedral. The example of this one is methane. Okay, here we have 4 attachments. They can all be electron pairs, or they could be 3 atoms and 1 lone pair. Your electron pair geometry is going to be tetrahedral. Your bond angle is going to be 109.5 or around that. It's going to may vary depending on what you have attached. So it may change it just a little bit. In this case, if it's a lone pair that's up here and you have 3 attachments, like in the case of ammonia, that lone pair pushes things down. So now you form what we call trigonal pair metal, right? So basically, if you kind of turn this flat, turn it in this direction, it looks like a little pyramid. And I'll show you a picture of that here in a second. Okay. Here, again, if you have 4 things attached, it could be, in this case, 2 atoms and 2 lone pairs. So this guy would still be tetrahedral because you have 4 attachments, right? You have lone pairs. Your lone pairs are going to act as attachments. Your bond angle is going to be 109, and then you're going to have a bent structure in the case of 2 atoms and 2 lone pairs. So here we have these 2 lone pairs that you don't recognize when we're doing our molecular geometry. So then we say our molecular geometry is going to be bent. Okay, so they're going to be bent towards each other. It's going to look bent because you don't really recognize those lone pairs when you're talking about the molecular geometry. And then an example of this is water. So water is going to be bent. Okay, so you guys got that, right? You can understand what I'm talking about?
Yeah.
Don't cry yet. Don't worry.
All right.
Okay. So just to be sure, because you know, one figure ain't good enough, you got to get them all, right? And this will kind of explain it a little clearer. Tetrahedral. An example of that is methane. You have 4 atoms that are attached. So your molecular geometry is going to be tetrahedral. And then your electron pair geometry is also going to be tetrahedral. Electron pair geometry, tetrahedral. The molecular geometry is tetrahedral. Okay? And it shows you this, anything that looks like this is going to be tetrahedral. Piece of cake? So 4, if you have a total of 5 atoms, you have 1 in the center, and then you have 4 things that are attached, tetrahedral. Center atoms, total of 5. 1, 2, 3, 4, 5 things, right? You have 1 in the center, and then you have 4 things attached. Oops. Got it? And the biggest thing here is that there's no lone pairs. Okay? So here, trigonal planar has 1 lone pair. It has 3 atoms that are going to be attached. You have a total of 4 atoms. Okay? So total of 4 atoms, 1, 2, 3, 4. You have a center atoms, you have a lone pair attached to it, and then you have your 3 atoms also attached. That's going to be trigonal pyramidal. Bent is going to be 2 lone pair and 2 atoms attached to a center atom.
What?
So, piece of cake?
Yeah.
So, tell me, what is the electron pair geometry of all of these guys?
Tetrahedral.
Tetrahedral. Okay. I know I said it right there on the slide, but sometimes I just want to see if you guys are listening to me. Because I love my voice, but, you know, it's boring a little bit. Okay, so a lot of times we need to draw our diagrams to make it easier for us to see. The best way of drawing our diagrams to make it easier for us to see that 3-dimensional structure is to draw what we call the wedge-dash diagram method. Okay, the way I like looking at it, so you have one that's going to be coming out towards you, right? And that's going to be your big band. And I'll show you, it's going to be a wide band, full solid color. Then you're going to have one that's going to be in the plane, that's right next to you. And then there's going to be one that's going to be behind you, right? And of course, you have the one that's going to be on top of you, right? So one in the plane, one on top, one that's coming out in front of you, and one that's coming behind you. Okay, so this is for tetrahedral. So the one in the plane is just going to be a single line. The one on top of you is also going to be a single line. The one that's going to be coming towards you is going to be like a growing triangle, solid growing triangle. And the one that's going to be behind you is going to be like your Wi-Fi bars, right? And you guys are saying, what the hell is this guy talking about, right?
Internet, Wi-Fi bar.
Wi-Fi bars.
Yeah.
Okay, so here's my example. So we have in, and so if we draw our Lewis dot structure of this guy, it would be okay, so this guy, this big, thick triangle, that one is coming out towards you. This one is going behind the Wi-Fi bars, or going behind, and this one is in the plane. It's in the same plane as that. Do you guys see that?
Yes.
Okay, here's a hard question for you. What is the electron pair geometry?
Trigon. You said that.
Electron pair geometry. What did you say?
The
Uh,
trigonal pyramidal.
that
Pair.
trigonal-
Not the molecular geometry,
No.
the electron pair geometry. So that means that you include the electrons and the number of attachments. How many attachments? So we're saying that this is one attachment, 1, 2, 3, 4. So if I have 4 attachments, what is it going to be?
Wouldn't it be tetrahedral?
That is correct. So your electron pair geometry, your EP geometry, if I can spell geometry, is tetrahedral. Okay, now, what is our molecular geometry?
The let me see. Trigon.
Trigonal.
1, 2, 3. There's no trigon.
Trigonal?
No.
Trigonal what?
Trigonal pyramid.
Pyramidal?
There you go. Thank you. Yes. Pyramid. Yes.
Piece of cake?
Dr. Henry,
Yes?
for the molecular geometry, is it because of the little dashes? That's why it's called that?
The molecular, no, it's called the molecular geometry because you're not looking, even though that your electron pairs have an effect on the shape, you're not looking at the electron pair. You're looking at the molecule as a whole. Here, you're
Okay.
taking everything into account. You're taking all the bonds here, and you're taking your electron pair into account as well. So that's why we call the electron pair geometry, and then you have your molecular geometry.
Oh, okay.
Okay. So here, you notice we don't show any of the lone pairs or anything like that. But when we draw our
No,
Lewis
so
dot
it's called
structure,
different, right?
yeah,
It has
these
a
are the
different
same
name.
thing. They're the same thing, but this just doesn't show you your molecular. It doesn't show you your electron pairs, right? Electron pairs are not normally visible because they're just attached to that nitrogen. They're not involved in bonding, right? So
I didn't pay
molecular,
attention to
you're
the.
looking at the
I
things that
didn't.
are bonded. What was
I
that?
didn't pay attention to the EP. I didn't know what the EP stands for a second.
Okay.
Thank you.
So you'll also see it'll say Vesper geometry. That means your electron pair geometry. You'll also see it written as that.
Okay.
So which is valence electron pair, valence electron pair repulsion. Okay.
So for a question on an exam, it'll just say like draw the wedge-and-dash diagram for nitrogen
Yep.
trichloride.
Yep.
Okay.
And then it'll ask you what is the electron pair geometry and what is the molecular geometry.
Are you gonna write just EP or are you gonna write the whole thing?
I'll write the whole thing.
Okay.
I just use EP because I get tired of typing electron-pair geometry.
Okay.
Okay?
Mm-hmm.
Questions, concerns? Anybody want to donate cash to a very worthy cause called Dr. Henry? Okay. Questions? No questions? Okay, so sometimes we'll have more than one center atom. So then we have to take in consideration the bonds and the shape of each of those center atoms and how they're going to affect each other. Okay? So can you guys do me a favor? Draw the Lewis dot structure of this compound and then draw the wedge-dash diagram for this molecule. And remember, oh, let me say one more thing before you guys get too heavily into this. So in this case, the only time that you need to sit there and draw something coming in and out is if you have a three-dimensional structure. If it's in a planar, then you don't have to draw something coming out towards you or coming in towards you. You just draw it all in the same plane. Okay, so if it's trigonal planar, then it's all going to be in the same plane. If it's linear, it's all going to be in the same plane. But if it's tetrahedral or trigonal pyramidal, then you're going to have to draw it in something coming in and something coming out. You guys get that?
I don't know.
Okay, we'll see. And then also draw this one for my benefit. We'll make you draw.
Oh, there you go.
And
Dr. Henry, you
yes,
know,
sir.
right now all the videos like this, how do I put in the top?
What do you mean?
Yes, to go like that rather than go like this, so I can see what is the element that we have to do it.
Oh, the periodic table?
Mm.
What?
No.
I guess I'm confused. What are you asking?
You know the video right now and my screen is like this. It's a column.
Ah,
I'm gonna put
so
it, there you go.
did you change it?
No, I haven't changed it. It's show to my video. I'm looking right now. Speaker video.
It's your settings. Your settings are set up, so it's flipping your screen.
Okay.
Is that happening to everyone?
What was it?
My
His,
screen is fine.
His screen is shifted vertically. So it's all, it has everything.
Yeah,
so
no,
it's
mine's
flipped.
fine.
Mine's fine too.
Okay. So it's his setting. Because I have the option of making it so that you guys are all in pain and flip my screen. And you guys also have that option by playing with your settings.
I will fix it. So,
Dr. Henry,
Yes, David?
when we're done, can you help us or help me with them? Because I'm still kind of like unsure.
Okay.
I'm
Yeah.
lost.
No, I'm not just gonna go on, you know. I do push you guys in the water and want you to swim. I'm not gonna let you drown.
You let me drown last night.
I didn't let you drown. You were
I'm
fine.
just- let me stop.
Like I kind of get it because of the distinguished differences of the two from the other PowerPoints. I just don't know how to understand to know that this is the molecular geometry
Okay.
of, you know.
Okay. So you guys just let me know when you've completed the three, and then we'll talk about it. Oh, we should also do this one. I have one more I want you to do. No, no, no. Hey, off. OFF. You get it? Dun, dun, dun.
Yeah.
You're so corny.
Hey, how we doing?
I know you're okay.
Guys ready? Meat and potatoes?
Let's
Okay, let's start off with the one that was given to us. Since it's a piece of cake, right? This one. Start off with that one. Okay, so what am I going to do? I'll tell you what I do. I always like starting off with the Lewis dot structure. That always kind of gets me what's going on there.
Count how many elements of each you have.
Okay,
So you
I have 4 elements total.
how do you see 4?
Oh, I'm sorry, 6. 6 elements. 6.
Is that because of the 2 carbons and the 4,
Orange.
whatever the?
That's right. 2 carbons and 4 fluorines.
Okay.
Judy's
All right, that
just
makes
keeping
sense.
me in check. Okay.
Huh?
You know it.
Yep. Okay. So then, what am I going to do? Who's going to be in the middle?
Do you put 2 carbons?
Carbon.
I put carbon.
Carbon. So we're going to put carbon in the middle. Just one carbon, or are we going to put both of them in the middle?
You put them beside each other.
Okay. Okay.
So we do the Lewis dot structure first, and then we move on to the
Yep. That's what I would do.
molecular geometry. Okay. Does the valence electrons also count into this too? We find out how many we are using.
Yep. So how many valence electrons do we have?
I got 36.
Well, let's do each element. So we have 2 carbons. So 2 times what?
4.
2 times 4 plus,
4 times
how many does fluorine have?
7.
7,
7, and we have how many fluorines?
4.
4.
Okay, so 4 times 7. Try to be consistent here. So 4 times 7 is 28, plus 8 is 36.
Mm-hmm.
Mm-hmm.
A lot to work with, but we know fluorine is greedy, right? Fluorine's a bully, so that makes it easy. So fluorine always wants to just basically have a single bond, unless it absolutely must have a double bond. So it's going to go, bam.
For all, like, so carbon would share like 2 on each side.
Let's see, bam. So carbon would share 1 fluorine,
fluorine.
1 electron with fluorine, because fluorine only needs 1 to be a noble gas, right? Because it has 7 already.
Mm-hmm.
So it's going to share 1 with that carbon. And think about fluorine. Fluorine's a bully. He's going to get his first. So then that leaves 2 electrons here for it to play with. So we'll do this. We have bam over here. Okay. And so that bring this electron over to here. So for our carbon to reach its octet, it's going to have to share 2 electrons between itself, right? Since that's 2, 4, so it's going to have to share these here. Piece of cake?
Yeah.
Okay, so this is the electron configuration, right?
Mm-hmm.
So this also helps us understand our electron pair geometry. So if we were drawing just the geometry, how would we draw this? Well, in this case, you just don't worry about the lone pairs. You don't show your lone pairs. If we're, I'm sorry, molecular geometry, we won't share our lone pairs. Are we going to have anything coming out towards us? or anything above us or behind us or?
Yes.
No, it's all going to be in the same plane. Okay, let me tell you why. Well, at least for the carbons, it's going to be in the same plane. For the fluorines, technically you do, but since we're not for the molecular geometry, we're not drawing any of the lone pairs, so we don't have to worry about it for that, okay? For the molecular geometry. Okay, so let's talk about the carbons. How many different things is it attached to? Now, the double bond does not count as two attachments. It counts as a single attachment, okay? So how many different things is this carbon, carbon A, attached to?
Three?
Or three.
Three?
3. Okay, so it has 3 attachments. So since it has 3 attachments, what type of geometry are we going to have? What type?
Tetra.
Trigonal.
Right. Trigonal.
Trigonal. You have 2 choices. It's either planar or pyramidal.
Planar?
That is correct. It's trigonal planar. So that means that the angle between these is going to be 120. And they're all going to be in the same plane. Hence planar, right? That's why we say trigonal planar. 120 and 120. Now what about B?
Is it the same?
Exactly the same. It's also going to be trigonal planar. So they're going to be exactly in the same plane. Piece of cake?
Yeah.
So you don't have to draw any wedge or dash or anything like that, right? This is it. This would be your answer. Piece of cake?
Are we supposed to know that it's going to be 120 degrees?
You should know the angle. Yes, because you have 3 attachments. 3 divided by 360.
Oh, I'm so slow. Okay, got it.
It's okay. That's why you got nice shoes, right?
Sure.
It's a bad joke.
I'm waking up. Let me get there.
Okay. Okay, so let's do another. Let's go with this guy. Okay, BCl3. What is the Lewis dot structure going to look like? You guys are so loud, you just won't stop talking. Jeez, I just have to keep telling you to shut up. What's going on?
1, 2, 3.
Boron be the center atom?
Boron will be the center atom. So that means we have CLs going around it. How many valence electrons does boron have?
3.
3.
How many does each of the CLs have?
7.
7.
And there's 3 of them times 3. So we should have a total of how many?
21.
Total 24.
Yes.
Okay, so now here's the hard part. What do we know about boron and those halogens when they come together?
Boron is an exception.
What'd you
How
say?
many valence electrons?
That's right. Boron is an exception. That is correct. It doesn't necessarily, it's okay with not having its octet fill. It actually kind of prefers to only have 6 around it. So how many bonds are we going to have? So we have 3 electrons, 1, 2, 3. We have 2, 3, 4, 5, 6, 7. 1, 2, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So for everybody to, for boron to have it, it's 6, and everybody else to have their octet, what do we need to do? How many electrons should be shared between chlorine and boron here?
2.
2 electrons?
Mhm.
Okay, so just a single bond?
Yes.
I put a double bond.
Nope,
Did
not
I?
a
No.
double bond. Because boron only wants to have 6, especially when it gets with the halogen. And all your guys, all your halogens, they only need 1 electron. They really don't want to share in the first place. So at the most, you're going to get that 1 electron that's typically by itself is the only one that they're going to include in the bond. Only time that they'll actually share more than that 1 electron is when they're kind of messing with other halogens. Okay? And that's usually fluorine. And that's only if they absolutely must do it. Most cases, they don't. It's always a single bond. Because if you think about fluorine squared, does that make a double bond? Isn't it just a single bond?
Mhm.
So almost 99.99% of the time, anytime that you have any halogen, halogens are the ones that are just one away from being a noble gas, they're only going to want to share 1 electron. So they're only going to make 1 bond, kind of like hydrogen does. Kind of, okay? But for different reasons. Okay, so that's the way it's going to look. So what is the what is going to be the wedge-dash diagram going to look like?
Is it the one with the
Is it going to be planar? Or is it going to be 3D? In the same plane or 3-dimensional?
planar?
It's going to be planar. So then we're going to have what's going to be the angle between these 2 chlorines?
120.
No, it's going to be
That's correct, 120.
120. Oh, sure.
Because we have 3 attachments. 1, 2, 3. Piece of cake?
Yeah.
Okay. Let's do a different color. Okay, so let's talk about PCl. Who's going to be the center?
Phosphorus.
Mm-hmm. Okay, how many valence electrons does phosphorus have?
5.
5.
Okay, so we have 1, 2, 3, 4, 5. How many does each of those chlorines have?
7 valence electrons.
And we have 3 of those. So total, how many are we working with?
26.
Oh, total 26.
Okay. Is it okay if I erase this one here? Give myself a little more room to work.
Mhm.
Yeah.
Okay, so where I'm going to put my chlorines at? So you said 7 around it. Is that correct?
Yes.
Mhm.
Okay. Get it? So how many is fluorine going to share with this chlorine?
1.
I didn't say, did I say fluorine? Sorry. Phosphorus sharing with this chlorine. 1. Okay.
Mhm.
What about this guy?
One,
Same thing.
What?
What about this guy?
one.
And this guy have 2 by itself? Is everybody happy?
Mhm.
Yeah.
Yes.
Okay. So what is its EP? Electron pair geometry. EPG.
You have 4 attachments.
I have 4 attachments. That's 1, 2, 3, 4.
So
Because those lone pairs counts as an attachment for EPG.
yes,
Okay, so what is it going to be? 4 things attached?
tetra.
Tetra. Tetra what?
Tetra.
Hydro.
The other
That's
one.
right. Tetrahedral.
Hedral.
Hedral. Okay, tetrahedral. Okay, so what is its molecular geometry? And can we draw the wedge-dash diagram for it?
Yeah.
Yes. Okay, what's it going to look like?
Phosphorus in the center.
Okay,
And then it's just the 3 attachments for this one?
okay, 3 attachments. So we're going to have one that's coming out towards us and sort of down. It's really hard to color with without a stylus.
You're getting better though.
Thank you.
It's not easy.
So this is the part that I don't get. How do we know that there's like one towards us, there's like one behind us?
Because it's a 3-dimensional structure. It's kind of like a pyramid, right? Is a pyramid like a flat sheet, or is a pyramid like a 3-dimensional structure?
Okay. I get it.
And then we have 1. Okay, so what would be the angle here? This one's a little hard.
Still 120?
No, actually, it's a little off from 120. But
109.5.
but it's close. What was that?
Yes.
You said 109.5?
Yeah.
Yeah. So in theory, it would be close to 109.5 because of that, because these lone pairs up here, but it's going to be between the 120 and the 109.5 because this is not as strong as a full atom. Okay. And that's partially the reason why we get that pyramid going on, pyramidal action going on. But just good thought. You won't need to know the angle for that one. Okay, so that's what it's going to look like. But like a pyramid, which is really hard to do. I guess I should finish putting my CLs. CL. 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 Okay, piece of cake.
Sort of.
Okay, what about this guy?
Oxygen?
1, 2.
This is going to be my center atom.
Oxygen.
Oxygen.
To join meetings, please link a calendar in your Alexa app. I've sent a link to your phone with instructions.
Alexa, join meeting. Okay, so that's 2, 4, 6. Oxygen. How many does the fluorines have?
7.
7. How many bonds are going to be formed between the oxygen and the fluorine?
1.
1.
Okay. Is everybody happy?
Mm-hmm.
Piece of cake. So what type of structure is this going to be?
A flat one.
What was that?
Linear?
No, the flat.
A linear structure?
Ooh, this is a good one. So electron pair geometry is going to be what?
EP.
Tetrahedral.
Is that 180? Like that?
Tetrahedral. So this guy's going to be tetrahedral, right? This EP is going to be tetrahedral. So what is its molecular geometry going to be?
Would that one be linear?
Nope.
No.
Set you up. Because you thought it was going to be linear, right? I set you guys up good
Yeah.
too. So why isn't it going to be linear?
It says 180.
Is it the lone pairs?
The lone pair. We have 2 lone pairs. So they're going to cause this to look like this.
I see. Okay.
So we call it angular or bent.
Then
Piece of cake?
Not really.
You say angular and what?
Or bent.
Dr. Henry, I have a question.
Yep.
So if the oxygen weren't to have those lone pairs, would it have been linear?
It would have been. But those
Oh,
lone pairs causes it to not be.
Oh,
If I do this one here, oops. Let's go. That guy, I'll show you real quick. That guy's going to be linear.
Oh, okay.
Because it doesn't have any lone pair on the center atom.
mm-hmm.
Cool?
Cool.
Cake?
No.
No.
I'll get there.
Okay, so let's move on. Everybody got it down? Can I erase?
Hear me, Dr. Henry?
I can't hear you. Now I can though.
So not all of them will have a wedge and dash diagram?
That's right. Now that's also part of it, right? Some of them will be planar. If it's planar, there's not going to be any Wi-Fi and triangle, right? Only if it's tetrahedral, trigonal planar. I mean, not trigonal planar, trigonal pyramidal. So if it's planar or linear, you don't have to worry about the dash or the wedges, right? So this is called your wedge, that's your dash. You just draw it in the same plane. So kind of like these guys here. This is planar, so all you have to do is just draw the line.
Hi, sweet Carol.
Any other questions? Okay,
What are you doing up here?
I can erase.
What are you doing up here?
Dr. Henry.
Yes.
Okay.
Here, did you have a question about something on the board?
No, like on the calling CIPC and C. That's the name called Tachahedro, Hejo, Techahedro. Those is the
Tetrahedral.
name.
Yes,
And
that's the shape. That is the shape.
the shape
So-
called, and then the bad one and the CI is called 3D.
The 3D one, so that one is called trigonal
Trigonal, okay.
pyramidal.
Trigonal pyramidal. And then how about a B? It called a
Hold on.
3D dimension, 120. Oh yeah, write them down to a picture. Trigonal pyramid.
Yeah, so for B, so this guy, 1, 2, 3. So this guy would be trigonal planar.
Okay. And then the F can be Aquila.
So both of these guys, hold on. And that's an L.
And did you call it 3D something earlier? 3 dimension?
3-dimensional. So this isn't a 3-dimensional. This one is planar. So this guy here, this here is linear. This one here, this one is angular or bent.
Okay.
This here, since we're looking at the electron pair, so we'll say EP. EPG is going to be tetrahedral.
Okay.
Okay, piece of cake?
Yeah, got it.
Okay, again, this is your EPG. Okay, ready? Ready to move on?
Yes.
Okay, polarity. So now we've talked about bond polarity. Now we're going to talk about molecular polarity. We talked about it a little bit last night, but during the day we didn't get a chance to talk about it. We're going to talk about it right now. So don't you fret. Okay, so we're going to look at bond polarity. I'm going to explain it using chloroform, which is Cl4. And you guys remember what CH4 is?
Is that methane?
Methane, yes. Okay, and then some variations of it, right? So I'm going to show you what they look like. Okay, so here's our chloroform. So we have CH4. So here we're just going to replace one of those Cl's with an H. Okay. So here we have the bond between carbon and chlorine. Chlorine is the one in yellow. The bond between carbon and chlorine. If you guys look on the electron negativity table, or just kind of look at the periodic table, who is closer to becoming a noble gas, chlorine or carbon?
Chlorine.
Chlorine. So who's going to want an electron more, chlorine or carbon?
Chlorine.
Chlorine, right? Chlorine's going to want it more because he's like, I'm right there. I am right there. Carbon's like, okay. So since that's the case, carbon is going to let chlorine take it most of the time. Or I should say, chlorine is going to take it most of the time because it wants it really bad, right? So that's talking about the bond, okay? So each of these guys are pulling on carbon exactly the same way, since they're all exactly the same. So it's kind of like, what is it? What do we call 4?
Tetra.
Tetra. So tetruplets, is that what they call? Or are they called quad? So they use quadtuplets. So it's kind of like having quadtuplets dating the same girl, right? So they're pulling all evenly on all sides. So one's pulling up here, one's pulling in front, one's pulling in the back, and one's pulling to the side. So all even on all sides, right? Because they're pulling evenly on all sides, even though that the dipole moment is going in this direction, and this is called a dipole moment. It shows you the way that the electron is going, and this is partially negative, and this is partially positive. And the dipole moment is being pulled in this direction here. And the dipole moment is being pulled in this direction. And the dipole moment is being pulled in this direction, right? Since it's being pulled evenly on all sides, the overall dipole moment is going to be 0. It's going to be a net 0 dipole moment. So then it's not going to have one, right? So that would be your molecular polarity. So it's not polar. This molecule will not be polar at all because you're getting equal pull in all directions. Okay, you guys get that?
Yeah.
Okay.
So I'm sorry. If you see the CL4, can you just make that assumption that it's going to be pulled equally?
Equally in all directions? Yes, you can, because you're assuming, in that case, you can make that assumption because that carbon is always going to be in the center, and at every pole, you're going to have a Cl. Cl has the same strength, so it's going to be exactly the same. Now, if we add fluorine and Cl, it's going to be different. Or, in this case, if we change one of those chlorines to a hydrogen, well, hydrogen isn't as strong as chlorine, right? So then what's going to happen is that because of that, hydrogen has less of a pull. Basically, these guys are going to be about the same as carbon, and hydrogen. They have about the same pull on each other. So these guys are just going to take that electron. They're going to try to be taking those electrons from carbon, right? These guys aren't going to really play a part. So in that case, you got a pull going this direction, a dipole going in that direction. You have a dipole that's going in this direction, and a dipole going in this direction. Okay, so then if you look at the entire thing together, if you sum up all of those dipoles, the molecule is being pulled between those two. So overall, you add up the sum of them all together, they're being pulled towards that direction. Where remember, these are guys are being pulled in opposite directions evenly. So then that means that in that case, no dipole. Here we have a net dipole of this direction. So the molecule is polar. You guys see that?
Yeah.
Okay, what happens if we change 2 more? We have 2 hydrogens here and 2 chlorines here. Look at the bond dipole. So if we look at the bond dipole between carbon and chlorine, what is that going to be? Which way is the arrow going to face? The electron going to go to?
That way.
The chlorine.
It's going to go towards the chlorine. What about this for this chlorine right here?
Towards the chlorine.
Okay, so these guys, they're not going to play too much of a part. They're just going to be giving up electrons essentially, because now this guy here is going to have a little bit of a pull, and it's going to want to get an electron to kind of bounce itself out. So where is going to be the net charge if we have a pull going in this direction and a pull going in that direction?
Would it be negative?
Okay, so is it going to be polar? Is the molecule, it's not going to be negative, is the molecule going to be polar? Because it's never really negative because it's one molecule together. You're just shifting where that electron is going to be going, right? So the molecule itself is going to be, it's going to have a partial negative charge, but it's going to be between the two chlorines because both of those are pulling. So it's going to have a negative, not a full negative charge, a partial negative charge going between the two. Do you guys understand what I mean by partial?
No.
Okay, so 1, you have 1. 1 is a whole number, isn't it?
Uh-huh.
Is half a whole number?
No.
Is 1/3 a whole number?
No.
Is 1/4 a whole number?
No.
No.
Okay. So if you and your boyfriend share a car, do you have a car?
No.
Or do you share a car? So you can drive it anytime you want to, right?
No, you can't drive it anytime you want if you share a car.
Okay.
You're the boss and you run things.
Unless you're the boss and you run things. See, that's different, right? Okay. So in the case of you're sharing something with somebody, you're sharing, right? So you're not getting it completely all the time. So it doesn't have a complete charge associated with it. You're sharing it, right? So in the case, hydrogen is getting it, or in this case, this hydrogen is getting those electrons 1/4 of the time, where the chlorines are going to be getting it 3/4 of the time. It's not complete. It's not a full charge, right? It's only partial. Do you guys understand that now?
Uh-huh.
You guys never thought you would work with fractions ever again, didn't you? Okay, so that's what that means, right? So what we're saying is that these hydrogens now are going to have like these partial positive charges. They're not completely positive. They're only partially positive because the electrons are being pulled towards these chlorines. And so overall, if you look at the overall charge, you're going to have a negative overall charge going between it, right? A negative partial charge between them. Not a complete charge, but it's only partial. It's not 100%, right?
Mm-hmm.
So it's not like an ion. An ion is like 100%. I'm 100% negative, or I'm 100% positive. These guys are only partially, okay?
Mm-hmm.
So anytime that you have a dipole moment, right? You have a net dipole where one side seems more positive than the other. That means you are polar. This one, since you're being pulled evenly, it has no polarity associated with it. So it's nonpolar. So this guy, nonpolar. And then these guys are all going to be polar. Okay, so if we have 3 hydrogens, right? So these guys are going to end up being partially negative, and then this guy, partially positive, and these guys are going to be partially negative. That delta means, it's like delta means change. So it's not a complete change, it's a partial change. We take it as meaning partial, not completely, right? So it's partially negative, partially positive. So your dipole moment is going towards that negative, right? So your electrons are being pulled in this direction. And since these guys are physically connected to each other, they're sharing, right? They're not giving or taking. That's the reason why it's always going to be partial. It's never going to be a full negative. Do you understand?
Mm-hmm.
Okay. So in this case, These guys are also going to be nonpolar because they're all even on all sides. Piece of cake?
Yeah.
Okay. Now let's see. We'll see if you guys understand anything that I'm talking about. So this is called, again, molecular polarity. Each individual from this carbon to this chlorine, that is called bond polarity. The overall bond polarity, bond polarity, bond polarity, the pink, that there is called molecular polarity. Okay, get it?
Okay.
You see the difference between the two?
Uh-huh.
Okay. Anyone else get it?
No.
I'm not getting this 100%, Dr.
Okay.
Henry. I'm paying attention, but some of it's just kind of going over my head.
Okay. I appreciate the honesty. It helps me to have the honesty. So let me see if there's a better way of saying it. Okay. So, Matt, let's say you're dating 4 women. Okay.
Okay.
Okay, so you're dating 4 women. Now, you give all 4 women equal amount of time, right? So in the case where you give all 4 women equal amount of time, are you favoring any one more than the other?
No.
Okay, so that's the case of being nonpolar, right? You have no favorite.
Okay.
Okay.
All the same.
You said you're the same. You date 4 women and you give them all equal amount of time.
So
That's a
no
good
polar.
thing. So that's nonpolar, right? So it's nonpolar. You have no favorite, right? Now, here, you're dating 4 women. But one you really don't like so much, you're just kind of keeping around because she's real pretty, like she's arm candy, you know? And then the other 3 have really cool personalities. They're cute. They have really cool personalities. So you like spending more time with them, right? So you take that time that you're getting from that one that's just arm candy, you know, you just use her when you have those special events to go to and you want to look, you know, like, man, look at the girl I can get, right? The other 3, they're the ones that you want to spend time with, right? So you take the time from this one and you're giving to that 3. Are you favoring those, the 3, compared to the one that you don't really like so much? She's just arm candy.
Yes.
So then you're putting your arrow between those 3. So you're sharing that time between those 3 and kind of neglecting that one, just spending only, you know, those special events with her. Do you see that?
Okay.
Okay. So that's what's happening here, right? And so in that case, it's polar. You have a preference for 3 of them and you don't like one, right? So much. Okay. So that's your polarity. Okay. Now, in this case, you have 2 of them that you don't like, but 2 of them that you really do like. So you take the time for those 2 that you don't like so much, you just hang out with them every once in a while. Oh, I'm going to hang out with them, you know, maybe an hour a week or something like that, where you take their time that you would normally spend with those and you divvy it up between the 2 that you do really like. Right? So again, do you have a preference?
Yes.
Yeah. To those 2 that you like.
Right.
Okay. So in this case, you have 3 of them that are just like, you know, so you give them an hour a week. And then there's one that, I mean, she has it all. She has the body, she has brains, she can hold a conversation. Your parents like her, right? But you're still keeping the other ones, you know, just around because you want to say that you're dating 4 women, right? So is there a preference?
Yes.
And so the dipole moment goes towards that one.
Okay.
Right? And then this is the case where you don't like any of them, right? So you basically spend an hour with each of them a week, you know? And so in that case, again, no dipole no dipole moment because you don't like any of them, okay? So you don't have a preference towards either one. So either one that's going to call you, you're going to give them all equal amount of time.
Okay.
Okay, does that help?
Yeah, that's a little bit easier to understand.
Okay. What about everyone else? How do you guys feel about Matt dating 4 women?
Not bad.
Mhm.
Thing, man.
Okay. Everybody else on the same page?
Yes.
Okay. So when we talk about polarity, so this is a case where we have 3 things that are attached. So carbon dioxide. So in this case, remember we just talked about this, carbon dioxide, where you're being pulled evenly on both sides, right? So you're in the middle, 2 girls, you're in the middle, they're pulling you evenly. Do you have a preference towards either one?
No.
No. Okay. So in that case, that one is non-polar because you're being pulled evenly on both sides. Here, this is what's really happening in the case of water. You have your dipole, you have your lone pairs. So you have hydrogens, and then you have you, right? And on you, you're really into yourself, so you want to give yourself more time. And plus take some of theirs, right? So in that case, you're pulling all the electrons towards you, right? Because you want to be the center of attention and everything like that. So in that case, you're thinking about you think about you, and the girls are thinking about you all the time, okay? So then you're the center of attention, so you have the dipole moment.
So that one's polar?
So that one's polar.
Okay.
Questions? That means yes, right? No questions.
Yes, no question.
Okay. Okay. So we have organic and inorganic material. This is my favorite topic. Are you guys ready?
Yes.
Yep.
Good. Good. Okay, so organic. So how many of you guys go to the grocery store and you buy organic vegetables?
I try.
Yeah, try.
Not within my budget.
Okay, so for those who try, great. I think it's great. But your definition of organic is incorrect. I'm going to tell you now. So the definition of organic basically means it has carbon in it. So compounds that have carbon in them are considered to be organic. They kind of behave kind of weird because carbon's a little bit of a whore, right? And how it interacts, it makes it interesting, right? We also know that carbon is the center of life, right? So a lot of our living particles are made up of carbon, so they're organic chemicals, okay? Inorganic chemistry or inorganic basically means that you don't have carbon in you, okay? Now, there are some carbon material, depending on who you talk to, right? They will call it organic, or they'll call it inorganic. Like for instance, carbonates, like hydrogen carbonate, bicarbonate, right? You guys know what sodium carbonate, sodium bicarbonate? You know what sodium bicarbonate is?
Baking soda?
It's baking soda, right? So some people say, well, that's not organic, but it has carbon in it. Really, it is organic, okay? Some people say cyanides, they're not considered to be organic, but they're organic, they have carbon in it, okay? Carbon dioxide or carbon oxides, organic, they have carbon in it. Okay, and so, but for the study of chemistry, depending on who you talk to, some people say, it isn't. But generally, the definition of organic molecule or organic chemistry is the study of things that have carbon in it. Okay? Simple?
Mm-hmm.
Okay. Inorganic are the things that don't have carbon in it. Okay? Okay, so I'm going to introduce you to what we call hydrocarbons. Okay? Hydrocarbons. Hydrocarbons consist of, what do you guys think it consists of?
Hydrogen.
And?
Carbon.
Okay, so anything that just has hydrogen and carbon are considered hydrocarbons. Okay, you guys got that? So, let's give you guys a test. Oops. Okay. This one. Is it organic?
Yes.
Yes.
Is it a hydrocarbon?
No.
This one. Is it organic?
Yes.
Yes.
Is it a hydrocarbon?
Yes.
Yes.
This one. Is it organic?
Yeah.
Hmm.
That's a C or a G?
That's a C.
Oh, okay. Yes. Has carbon.
Is it a hydrocarbon?
Yes.
Okay, we'll do a poll. Since I haven't done a poll in a while, right? Because I'm curious. What the hell? Hold on. Things are not working for me today. Come on.
Dr. Henry?
Yep.
The practicing test is open, yeah?
The practice test is open and your real test is open.
Okay.
And that one's due on Saturday?
Yep. Yep. Saturday at midnight.
Okay.
Or at 11:59. Sorry, 11:59 Saturday.
Does the practice test close after tonight, or is it going to stay up till Saturday?
I'll have it open till Saturday.
Okay. Thank
I'll make that adjustment. Remind me because I will forget. As I tell you, I'm old. So I realize sometimes I hate Zoom so much. What's the purpose of keeping my password if you're going to constantly delete it and I have to remember it? Let's see. See if that works.
That says it's due on Sunday.
No, it should be due at 11:59. Oh yeah. Yep. Okay, fine. I'll change it. I'll change it to Saturday.
No, you could leave it on Sunday.
That's all right. You know. Since you're complaining about it, you know, I want to kind of keep you guys happy. You know. Give me 1 second while I Okay, we'll just do a hand pull since it's not gonna let me do what I want to do. Okay, so how many of you guys think, and you got to put your things up here, put your dash. So how many of you guys think it's a hydrocarbon? And how many guys think it's not a hydrocarbon? So we'll say yes and no. So put your dash by yes or no. It's locking me out of my Zoom account.
I still don't know why can you feel why you how you feel
For the bottom one, right?
Yep, for the blue one.
And then
Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And is that somebody's 12? And we have 19 participants. So 7 of you guys aren't voting. Are you scared? Scared of being wrong? Give me your votes.
Oh, okay.
Put your vote down.
Let's see.
Come on, vote, vote, vote. Okay, well, we got enough. So the correct answer is no, this is not a hydrocarbon because it has chlorine in it as well. So that means it doesn't have only hydrogen and carbon. Piece of cake?
yes.
Okay, yes.
Okay, so now that we've established that, let me tell you about some of these hydrocarbons. So we're going to talk about things that only have hydrogen and carbon in them. There are 3 types of hydrocarbons. One is called alkane. The other one is called alkene. And the last one is called alkyne. Okay? Alkane are considered to be saturated hydrocarbon. The reason why we call it saturated is because it's saturated with hydrogen. That means that you have only single bonds of hydrogen and carbons. So what I mean by that is I'll have a C, a C, a C, a C, a C, a C, H, 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 H. So remember, carbon can have 4 attachments. So it's going to have 4 attachments, and it's going to fill those attachments with the hydrogens. So that's 1, 2, 3, 4 around this carbon. Oops, I forgot one. Forgot that H here. Okay, but you'll notice everything is a single bond. Okay, so A and E, anytime you see A and E, it probably means that it has only single bonds in it when you're talking about hydrocarbons. Okay. E and E means you have at least one double bond between the carbons. And these are considered to be unsaturated because you have double bonds. So when they're talking about saturated fats, they're just saying that you have all single bonds in that fat. Okay, so that's around here, that's 1, 2, 3, 4. So your 4 bondings, 4 things are around. So in this case, you have double bond here, right? So that's alkene. So this would be an alkene. And these represents families, right? Families of hydrocarbons. Alkanes, alkenes. So what do you guys think alkyne is?
A combination of both.
No, not a mixture of both.
Having more than 2 bonds?
A triple bond?
Having more than a double bond? You mean a double bond?
Yeah, sorry.
So in that case, if you have more than one, than a double bond, you have a what bond?
Triple.
A triple bond. That's right. So if you have at least one triple bond in this compound, okay? If you have at least one triple bond in this compound, it's going to be an alkyne. Okay, you guys get it? Simple. One double bond, at least one double bond, alkene. One triple bond, alkyne. No, none at all, not a single one, alkane. Got it? Okay, we're going to see. So I'm going to show you something real quick just to save me time. Often we will draw, when we're working with carbons, we will draw what we call the stick structure. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this here, this stick structure in pink, is the same thing as this right here. Okay, it has each end represents a carbon, and since it's saturated with hydrogens, we know that it's saturated with hydrogens, So we're so lazy that we just don't put them down. So it's represented that it's only single bonds, because that's what the lines is representing. There's one carbon here, a 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 carbon here. So at each point, there's a carbon. So that's a total of 6 carbons. 1, 2, 3, 4, 5, 6. And they're saturated with hydrogens, so they're surrounded by as many hydrogens as they can. How many different attachments can carbon have?
4.
4. So if I have this carbon right here, and it's attached to another carbon, that counts as 1 attachment. So how many hydrogens will I have surrounding this N carbon?
3.
What about here? So I have this carbon here is attached to this carbon, and it's also attached to this carbon. So that's 2 attachments. So how many hydrogens will I have attached here?
2.
So this guy is going to have 2, this guy is going to have 2, this guy's going to have 2, this guy's going to have 2, and this guy's going to have 3, right? So look here, 3, 2, 2, 2, 2, 3. Okay? So exactly the same information given to us. Okay? You guys see that?
Mm-hmm.
Okay. So the way that we would draw, the double bond, this is the same way. Only thing, we'd go a double bond. How many carbons do we have here?
1, 2, 3.
3. So that's 1, 2, 3. So we know how many attachments can carbon have?
4.
4. So if 2 of them are dedicated to a double bond, that's 2 right there. So then how many hydrogens would I have here at this end?
2.
Okay, just like we have right here. So if I have 2 dedicated to the double bond, 1 dedicated to another bond, how many hydrogens would I have on the center carbon?
Just the 1.
Okay, and then here I have 1 dedicated to the attachment to that center carbon,
Mm-hmm.
and that's it. How many hydrogens would I have at this end?
3.
Okay, you guys see that? So the one in pink is the same thing. Oh, that did not work out the way it was supposed to. The one in pink is the same thing as the one in blue. These are exactly the same thing. Just 2 different ways of writing it. Come on. Not working with me at all today. Just trying to make it green. There we go. And then this guy is the same as that one. Okay, so I want you guys to use those intuitive skills that you guys have inherited from this class so far, and tell me, how would I draw this guy?
You would you have 1, 2, 3, 4 carbons, so you'd have 4 sticks.
Okay, so I'd have 4 sticks.
Yeah, but I lie. You won't have 4 sticks because you have a triple bond there. So you would technically only have 1, 2, 3. So that's 1, 2, 3. You would just have a triangle like this, right?
Like, show me where.
A triangle. Here, let me see if I do this right. This is. Can I annotate it?
Yep.
Okay.
Put it right here.
Okay. So what I did was in pink. I did something like, because you said that the triple bond is right there. So what I did is I went like that. So that's 1, 2, 1, 2, 3 carbons, and then I did like up here, but I put it down here again. But that was, I went something like that.
Okay, so would that work? So then that's 1, 2, 3 carbons. We have how many carbons here?
4.
We have 4. So that doesn't work out.
Okay.
Okay, but it's a good thought though, right?
Okay.
But you're on the right track. No, you didn't fail. You just forgot 1 carbon, right? You forgot to put.
Oh, okay.
Okay, 1, 2, 3, 4. So here, let's number it, because I'm looking at your faces, and your faces are telling me, what the hell is he doing? That's what your faces are telling me. This is our first carbon. This is our second carbon. This is our third carbon. And this is our fourth carbon. This is our first carbon. This is our second carbon. This is our third carbon. And this is our fourth carbon. Now, you want to draw your triple bond tighter together, because otherwise it'll look like it's branching off of each other. And I'll show you what a branch looks like here in a second. So I'm going to kind of clean this up a little bit, if you don't mind.
My bad.
All right. No, you did a good job. I'm not being too critical. Okay. So triple bond. So this is your first carbon. That represents that carbon right there. This is your second carbon. That represents this carbon right here. This is your third carbon. That represents this carbon right here. This is your fourth carbon. That represents your fourth carbon. You guys see that?
Yep.
Okay. Same thing going on up here. Let's see. 1, 2, 3. This is 1. This is 2. This is 3.
Oh.
You guys see that? And then here, 1, 2, 3, 4, 5, 6. 1, 2, 3. Oops, sorry, I'm screwing up here. 1, 2, 3, 4, 5, 6. Okay, piece of cake. Okay.
And then Dr. Henry, one question. What did you say, like on the bottom, the 1, 2, 3, 4, you've got those 3 lines from 1 to 2. What is that again? That's just talking about your triple bond?
That's right. It just represents a triple bond. 1, 2, 3 lines. This makes a double bond. 2 lines. 1 line, single bond. Right? And so what I said to her, I said, you want to be careful. You want to make it tight so it doesn't look like it's branching, because I'm going to show you what a branch looks like. So take a picture of this. Everybody got a picture? Got a picture?
No.
And so, and then what I would do is say alkanes, all single bonds. Alkenes, at least 1 double bond. Alkyne, at least 1 triple bond. Okay.
This one triple bond or single bond, okay.
Piece of cake?
Let's see. Let's see.
Okay, so you guys want to give it a test run?
Yes.
Yeah.
Okay. See how we're doing on time. Let's see. Share white.
Alkane or single bond. Oh no. Alkene. Oh, it's this wonderful. Oh, that's a lot.
Okay. Okay, this first one. Is it alkane, alkene, or alkyne? So we'll say, let me put letters on it.
Okay.
A.
Alkane.
Alkane.
Yeah.
Single bond.
A. Okay. Alkane.
So what I want you guys to do is okay, so A, is A alkene, alkane, or alkyne?
With A.
Alkane.
So which one is going to be an alkene?
B.
B.
Somebody said B?
Yeah, B. Yeah. No,
Okay,
no,
what-
C and D.
C and D?
Yeah, the last one.
So you're saying C and D. That's what you're saying.
Yeah, no, not here. I'm not.
No?
No, not
Okay.
here.
Not there? Okay. Oops. Oops.
Okay, yeah.
Okay, hold on.
That's B. Yeah, now.
Okay, so no D here. Is that right?
No, D10. Oh, they
Okay,
have the D2, I think so. They have D2,
you say D2?
the D2, B and D.
Okay, so here's the rule, right? Here's the rule. Because if you said, you guys just told me A, so what is the rule for alkanes?
Only single bond.
One single bond.
Only single bond. Okay, so let me explain a little more. Alkenes, right? It's considered to be an alkene only if it has only at least one double bond. It can't have a triple bond. Okay, so
then
you
it'd be an
can't have.
alkyne.
So it fall under the alkyne. So there's a priority, right? So alkyne has a priority over alkene. Alkene has a priority over alkane. Okay, so these guys have single bonds. We don't call them an alkane and an alkene. They can only be one or the other. It's like once you marry into that family, you can't go back. Okay. So who's an alkyne?
C.
C and D.
C and D. Piece of cake?
So, Dr. Bond, since the D here, they have like alkyl there too. How can we cannot put in the, with the alkyl, the D?
Because this one has priority. Alkyne is like the top of the top. So once you marry into the alkyne family, you can never be an alkene. Once you marry into the alkyne family, you can never be an alkene. So this guy is big boss, right? This guy is a lower boss. This guy is no boss. He's the lowest on the totem pole. Okay, you guys get that? So if I have, see, I have single bonds, right? So I'm not an alkane and an alkene. I am just an alkyne. Because I have single bonds and triple bonds. So since I have single bonds, double bonds, and triple bonds, I'm just going to be an alkyne because it has priority. Here I have double bonds and single bonds. Okay, so now my next question. How many carbons do I have in A?
We have 1, 2, 3, 4, 5, 6.
I'll give you guys options.
8.
9.
8.
So we'll go.
A.
Okay. So put your numbers where you think they're at.
1, 2, 3, 4, 5, 6. Which is 1, 2, 3, 4, 5, 6, 7, 8. I put 9. I go with 9.
You want us to mark where we think it's at?
That's right. Everybody vote?
Yeah.
Anybody didn't vote? What's the rule for the class?
Take a vote.
Gotta vote. This is the damn elections. You all are voting, right? November, you're voting. You're voting.
3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, I go with 10. No, I try it. I go with 10. Yeah.
What you want? We'll go through it here in a second. Are you
I'll
ready?
try one. Yeah.
So that's
Yo,
1.
what the fuck? I can't even see or hear anything anymore.
That's 2. That's 3. That's 4. That's 5. That's 6. That's 7. That's 8. And that's 9. So the correct answer is 9. What about here?
Oh,
How many carbons
uh,
for B?
1,
2, 3, 4, 5,
oh,
2,
5,
3,
6,
4, 5, 6, 7.
1,
8.
2,
You want us to vote?
Yep,
4,
vote.
5,
Let me put some more numbers up there.
1, 2, 3, 4. 1, 2,
Dr. Henry, the double bonds, they count like an extra?
Nope, double bonds don't count as an extra. You're counting the number of carbons. All I want to know is the carbons.
Got it.
How many carbons?
6. Right.
No, there's more than 5 people in the class, so.
Which one are you guys doing? I got kicked out.
B, how many
Oh.
carbons? Carbons for B.
1, 2, 3, 4, 5, 6. I say 6.
Some water?
No, I'm okay.
Okay, everybody agrees?
Mm-hmm.
Okay, let's see, that's 1, that's 2, that's 3, that's 4, that's 5, that's 6. So 6 is the correct answer. What about C?
8.
1, 2, 3, 4, 5, 6, 7, 8. Piece of cake. What about D?
1, 2,
6.
Okay, simple.
Mm-hmm.
Okay, let's see. Okay, so you guys know how to do alkenes, alkynes? Feeling good so far?
Yeah.
Yeah? You can tell the difference?
Yeah.
So how many hydrogens? The first one. How many hydrogens does the first one have? Let me put some numbers up there. Let me count.
Every carbon has 2 hydrogens, yes?
I don't know.
No, it's 1, 2, 1, 2, 1, 2. 18.
Okay, put your numbers where you think there are, then we'll go through them. And the question is,
There you go.
Fucker, dude.
okay, I like this. This is getting good. We're getting people voting. I love it. Are you feeling good about this? You want the answer?
What's the correct answer?
The correct answer is 20.
Ah, how do you
What?
get?
Let me explain.
There you go.
Okay, let me use a different color. So, well, let's not use that one. Let's use green. Okay, so carbon 1, carbon 6, carbon 7, and carbon 9. All of those are going to have 3. So 3 times 4. Then we have, let's use dark blue, carbon 2, carbon 3, carbon 5, and carbon 8 are all going to have 2. So that's 4. Let's say 2 times 4.
That looks like a 1.
Sorry, let me fix that. Just criticize my handwriting.
Sorry.
Okay, and carbon 4 has none because it has 4 attachments to carbons. So we add it together.
Yeah, it's 20. 12 plus 4. Or 12 plus 8.
Yeah.
Huh.
Okay, piece of cake. Okay, what about B?
So it's 1. Hey, what happened? I was using that for reference.
Oh, sorry. I got happy for like, yeah, they don't need it.
Okay, that's
I
good.
got a number that isn't there.
You got a number that isn't, oh, let me finish. So let's see. So let's change our scale here.
Oh, wait.
So let's do. Erase what you guys wrote down earlier. Okay, everybody got their vote in? Okay. Okay, so let's do it like this. We'll start with purple. So 1, carbon 1, 4, and 6. They're all going to have 3 hydrogens. So 3 times 3. Carbon 5. That's going to be 2 hydrogens. Carbon 3 is going to be 1 hydrogen. So the answer is 12. Oh, and carbon 7, I don't know why I made that a 7, or sorry, carbon 2 has none
Why it has none?
because it's attached, 4 attachments. It has this carbon it's attached to this carbon, and then it has double 2 attachments to this carbon. So it has C, double bond, attached to another C, attached to another C. So that's 1, 2, 3, 4. So it has no hydrogens coming off of it. Okay? I guess it's pretty bad when you can't read your own handwriting. Okay? So let's skip D. D's too easy. C's too easy. Let's do D. How many hydrogens there? Then we'll call it a day.
One.
Did you say 1?
No, I'm counting.
Okay. Let me erase these.
Thank you.
So
You guys are figuring it out. So we have our votes.
No?
Oh God. What? Oh no. I don't know. Oh, well, I go with A.
Sorry. Going to give you an opportunity to resubmit your votes because I have to fix something. All right. Yeah. Let's see. Come on. Okay. Put your votes in. Everybody's votes in. Okay, you ready? Okay, so 1, 3, and 4 all have one hydrogen. So that's 1 times 3. 2 has 0. 5 has 2 hydrogens.
What? The 7? Oh no.
And 6
3?
has 3.
Hey, yeah, I got it. Oh, God. Yeah. No.
So that's 8.
6.
Piece of cake? Okay.
Doctor,
Yes.
you know when you do the map, like 1 times 3 is 3, right? 0 times 1 is 1, 2 times 1 is 5, 3 times 1 is 3.
Uh-huh.
3, 4, 5, 6, 7, 8. What? 0 times 1 is 0. Yeah, okay. Get it. Now I get it. I
Get it?
thought 0 times 1 is 1. Yeah. No, give me 1 minute. Picture.
Okay. That's all I got for you today. Or this is where we're going to stop. There's always tons, but got to stop at some point. Feeling good so far? Not too much?
I'll learn one more time.
So I'll see you guys after the exam. Don't